going to be the Lamont precession frequency times the time, which is going to be gamma b, which is the Lamont precession frequency, times the distance through the coil divided by the velocity of the neutron. So this is just the distance that I'm talking about there. Now the b inside this coil here is actually some field value which it takes along the center of the field, plus some coefficient times some distance r away from the center here, plus some things here. So what we said last time was that if you then have a neutron which comes, let's say, off axis and a neutron that's on axis, there's going to be a slight difference in the field, and that difference in the field is going to give you a different phase integral. And you can correct that by putting some sort of Fresnel coil, Fresnel current distribution in the beam and just applying Ampere's theorem. So that's what happens with a solenoid coil. Now, remember, these solenoids are on an instrument, on a neutron scattering spectrometer. So we have a neutron beam coming through the solenoid. We have another neutron beam going out through another solenoid. And that's the setup that we have in this energy resolving spin echo device. We have a sample here, we have some incident wave vector here, and some scattered wave vector down here. Now, in fact, of course, there are different neutron paths that you can take through this this solenoid. You know, here's another one that gets you to the sample, and you can pick a lot of different ones. So if I draw the scattering triangle for this thing, let me draw it here. Let me assume for the moment that it's elastic, then elastic scattering, then I have an incident wave vector like this, a scattered wave vector like this, and a Q vector joining the two of them. Now there's, as I said, there are different paths that you can take through this instrument, defined maybe by slits that you can imagine that you put in here to define the beam trajectory. And also, of course, what one's done is to monochromate the beam before coming into this instrument. The monochromatization is not that good. We don't need very good monochromatization for spin echo, but nevertheless there's some degree of monochromatization, which means the length of this K vector can vary somewhat. So in point of fact, what one has, and I don't know whether I can draw this sensibly, but what one has is a kind of a little volume, a box on this that one can draw at the end of this K vector, and this point here is the average of all of the K vectors, but any other point is an equally good K vector. In other words, I can go from here to some point inside the box, and that's an equally good K vector, Ki vector that's going to get through my instrument. And then I have a similar box that I can sort of draw down here that is the final wave vector. If I can sort of draw a little sort of perspective inside the box here. So the scattering events, the scattering can take a neutron from any point inside this box to any point inside that box. So what you can see, of course, is that you have some energy resolution, delta E, which just involves the fact that you can have different lengths of this and different lengths of this vector, and it's the energy change is of the neutron is just proportional to the difference of the squares of these things. And also that there is some uncertainty in the Q vector, because the Q vector that you actually measure may not be from the center of this box to the center of this box. It may be from some corner of this box to some other corner in this box. So that's what you have. So this, of course, is usual drawing that you have for the resolution of a spectrometer. But what I want to point out is that you can also think of it as the transmission function of the instrument. That is to say, there are certain neutrons that can get transmitted. So if I now go over and plot what I actually get from some spectrometer like this, right, where I have different possible ingoing and outgoing trajectories, what I can see is that around this elastic scattering situation that I've depicted in the triangle over there, there's a range of values, both of energy and Q, which I can get through the instrument. And so any excitation or any source of scattering which lies inside this little circle or ellipse here is going to cause a signal in the detector that I put down here, right? So now I've got, and this I can call this ellipse here, I can simply refer to as the transmission function of the instrument, or the resolution function of the classic canonical resolution function of the instrument. So what does spin echo do? Well, what we saw from this is if we put in these Fresnel coils, then any trajectory that goes through this instrument will have a phase, a Larmor phase, which depends only on the difference in velocity between the ingoing and the outgoing neutrons. And we saw last time that difference of velocity is linearly proportional to the energy transfer. So that's what this is. This is energy transfer. So effectively, inside this little volume here, I can imagine that I have lines of constant phase like this, because the lines of constant phase don't depend upon anything except energy. They depend only on the difference between the velocity, the ingoing velocity and the outgoing velocity, and that, as I said, we saw last time, was proportional to the energy transfer. So if you like, you can picture this as some sort of corrugation inside the transmission function of the instrument. And what neutron spin echo does is to say, okay, that corrugation there is a cosine function, and I'm going to take whatever scattering I have inside that transmission function and Fourier transform it, do the cosine Fourier transform on it with a sort of corrugation, or cosine function that looks like this as you go across the transmission function of the instrument. And but you can see that the lines of constant phase are, as I said, independent of Q. They depend only on the energy change at scattering. So what we're going to talk about today is situations in which the scattering that you're interested in is not just dependent on the energy transfer, but has some dependence on the Q vector. And what it'll turn out is that in order to be able to use spin echo in such cases, we've got to relax this constraint that the boundary of the field region is perpendicular to the direction of travel of the neutron beam. You can see that in both of these cases, the boundary of these fields is perpendicular to the neutron beam that's going through them, direction of the neutron. Look at that again. So here I'm going to imagine that this light gray region here is the region over which I'm applying a magnetic field. And for definiteness, I'm just going to assume that I'm applying it into the plane of the screen. And instead of having my neutron come through this magnetic field region horizontally so that the boundaries are perpendicular to the trajectory, I'm going to have a trajectory that goes through the field at an angle like this, where this, I'm going to call this angle chi here. Now the Larmor precession frequency doesn't change with any of this. It's still the same gamma times the magnetic field, and so but the total Larmor phase, the total number of turns, if you like, or the total number of radians of turn, in point of fact, is still given by omega L times the time that the neutron spends in this field. But now the time that the neutron spends is given by this d, the distance between the two borders of the field, divided by the component of the velocity in that in this direction, which is its actual velocity times the sine of this chi value. So in fact, the phase depends upon the component of the wave vector now that is in this direction, which I've called k perpendicular. So we have a way, if you like, of using spin echo to label this wave vector rather than labeling the total wave vector of the neutron, which is what we did in the other situation. So what I'm going to show you is that these type of tilted fields that I talked about here can be used both for something called phonon focusing and then for small angle scattering. And the first one of these to be proposed actually was proposed by Ferry-Mezai for the so-called phonon focusing, which was an idea to measure the line widths of phonons, and I'll show you why how that works. It turns out that it's much easier to implement this method using this neutron resonance spin echo, and that's what has been built up after some tests in I think '98. They have installed this type of neutron resonance spin echo on a 3-axis spectrometer. I guess it's called the Helmholtz Institute in Berlin now, rather than the Hahn-Meitner Institute, and at FRM2 in Munich. As I said, that was the first use that was proposed, and I'll show you how that works. But another use is to code. Is to apply it to small angle scattering, or in fact to diffraction in general, and I'll show you again how that works. It can also be used to separate diffuse scattering from specular scattering in reflectometry. It can be used to measure in-plane order in thin films, and also to greatly improve the Q resolution in diffraction. I probably won't talk much about these, but if you're interested in them, there are papers out there, you can look for them. In fact, this so-called Larmor diffraction now achieves resolutions of the D-spacing, if you like, of a crystal, which are better than can be achieved with the best synchrotron X-ray facilities. So let's go back to this. Let's go on to this figure here. I told you, spin echo setup. You have this transmission function of the instrument here, and inside that transmission function, you have these lines of constant spin echo phase. So, supposing you have an excitation that you're trying to measure, and you'd like to know what the line width of it is, and the excitation has some finite energy. So here, imagine that you've got some Einstein mode, which has a constant frequency as a function of Q. So one question you might ask is, can you measure that? So here, down here, if you were making a measurement, what you would be measuring essentially is the line width of the excitation. And very faintly off on the right here, you can see the line width that you would measure if you were to simply translate this resolution function through a sharp excitation here. That wouldn't be very useful to you, but if you have this very fine phase grid that you inside the transmission function, you can do a Fourier transform of whatever's inside the transmission function and measure effectively this width. You won't measure it in energy, you'll measure it in time, as I showed you during the last lecture, but you'll effectively be measuring the lifetime of this excitation using this Fourier technique. So the question is, could you do the same thing when you have a finite energy excitation? So let's just check that. So if you could just bring me back to the board here, line width of that finite energy excitation. And remember, the total phase that you're looking at here is just going to be some constant times the field in the incident beam times the length of the thing in the incident beam over K1 minus B d2 d2 over K2. Now I'm back in the same geometry as I was before with perpendicular field boundaries in this thing. This is the first thing I'm going to do, and then I'll show you how to do the tilting. Now, if you're looking at some finite energy excitation, or you want to look at some finite energy excitation that is like this, all right, then what you have is that the outgoing energy of the neutron is equal to the incoming energy of the incoming neutron, the kinetic energy. I may be standing in your way on the blackboard, plus whatever the energy of this excitation is, E0. Now, so I can, if I look at that and I ask what the differential of that is, I'll get myself something which looks like, so let's see, I'll get K2 squared is equal to K1 squared plus 2m over h bar squared times E0. And if I differentiate that, I'll get 2k2 dk2 dk1 is just equal to 2k1 from this thing here. Now I'm going to look at this total phase, and I'm going to ask, under what conditions does that total phase not change when I change the incident wave vector? Right? So this is K1 is going to be my incident wave vector, and I'm going to look to see, because what I want is that whatever K1 I choose, right, whatever incident wave vector I choose, I'm going to have lines of constant phase that are going to line up like this. So I want actually that the phase, the total phase is independent of the incident wave vector and is only going to depend upon the energy transfer. So if I do that, I'll just have to differentiate this thing up here, and I'm going to get minus B1 D1 over K1 squared plus B2 D2 over K2 squared times dk2 dk1, and that whole thing is just going to be k into minus B1 D1 over K1 squared plus B2 D2 K2 over, K1 over, let me write that better, K1 over K2 cubed. And so if I put that thing equal to naught, what you can see is you're going to get essentially a solution which says that this is going to be true. B1, B2 D2 over K2 squared. And the number of turns, if you like, which I can just call N1, is the number of, or the phi, let me say phi 1, let me call it phi 1. Phi 1 is just going to be, is just this thing. So I've got, this is cubed. Miswrote that. So then I'm going to have phi 1 over K1 squared is equal to phi 2 over K2 squared. And so what that's telling me is that providing I set up these fields in such a way that this is true, right, then I will have these horizontal phase lines inside the transmission function of the instrument. And that, let me see if I can go back to for the phase angle in the first leg of the instrument. I've written it as N1, which is just the number of turns. So I can measure a horizontal dispersion curve, or the width of it, or the lifetime of it, if you like, by setting up the instrument so that I have different wave incident and final wave vectors, and setting them up using this equation. So actually the first time that real inelastic scattering was done, was measured using neutron spin echo, was when Mezai looked at the width of the Roton minimum in liquid helium-4. And you perhaps remember that the dispersion relation of liquid helium-4 is such that there's a low energy, essentially acoustic excitation comes up, and then there's a dip, and that dip, in the bottom of that dip, which is the Roton minimum, the dispersion curve is essentially flat, and by setting up the instrument in this way, with the fields chosen to be in this ratio, Mezai was able to measure the lifetime of the Roton in liquid helium.
Hey,
if that doesn't help you.
Hey, Roger, we have a question.
Yeah. Yes, sure.
Okay, so the question is, basically, what is N1 in that equation? We're a little lost. What is N1 and N2? And also the other thing, can explain, when you said the instrument will have to be set up in that fashion, maybe just explain a bit more what was meant by having to set it up. The field.
I apologize for that. So, this N was this is a view graph that I should have corrected it because I've been using phi as the phase, and this N was a view graph that I used when I just called it the number of turns, or the number of turns of the spin precession. But so I apologize for that. Just substitute phi, which is the phase that the spin gets in as it processes through the field, for this, and ignore my old notation. Just assume this means phi 1. It's the total phase of the spin as it processes. So what do I mean by set up the instrument? So let's supposing I choose a value of K1, which is the incident wave vector. Supposing I've got 4 angstrom neutrons coming in on my instrument, for example, and then K1 is just going to be 2 pi over 4. Now I know what the energy of the Roton minimum is from, let's say, from some triple axis spectrometry experiment. So I know what the value of K2 has to be so that I can position my transmission function of my instrument so that it's essentially over the top of this excitation, the Roton minimum. Now what this equation tells me is that I want the ratio of the phase accumulated in the incident beam to the phase accumulated in the output beam to be the ratio of the energy, the incident to the final energy. And of course the phase accumulated, since I'm not going to change the length of the magnetic field, the phase accumulated is just going to be proportional to the magnetic field. So what this tells me is the magnetic fields that I have to use in the front end of my spectrometer and the back end of my spectrometer in order to set it up this way. Did that answer your question?
Yeah, that makes sense. Now we understand.
Colin?
Yeah, I think we've got it. So basically,
but it doesn't help you much if you've got a phonon. So this is what you'd see if you had an acoustic phonon. You'd have a phonon mode that looks like this. That's just a normal phonon that you'd see. And here is, let's say, the resolution function of a triple axis machine. And as you may, I don't remember whether you've already looked into triple axis machines yet in this course, but Brockhaus invented this method called the constant Q method, in which the transmission function of the instrument was simply scanned up at constant Q through the dispersion curve. And you can see that if you do that, the width that you're going to get is something like the width of this resolution function. In other words, you're not really going to be measuring very accurately what the width of this excitation is, i.e. what its lifetime is. And so what you'd like to be able to do is, of course, is to make these constant phase lines parallel to the gradient of this phonon here, because then when you do your Fourier transform, the phase is changing in this direction, and that's perpendicular to the phonon dispersion curve. And so let me just show you that you can do that essentially by tilting these fields. So let's just go to the blackboard again. So I showed you a picture a little while ago in which I had a scattering triangle, and I put some, if you remember, so it was like this. Let me just draw this. So this is, let's say, KF. This is KI. And we've got some Q vector down here. And each end of these, we've got some volume of space, which is of the wave vector space, which corresponds to the transmission of the instrument. Now, if I have these, if I have in a normal situation, the one I've been talking to about up till now, all of these constant phase lines are like this, right? Because they only depend upon the length of this vector, right? But if I tilt the fields, then what I showed you before was that the constant phase lines are essentially depend upon the direction, the tilt of the field, because I'm only encoding one component of the vector. So what I'm going to have is some set of phase lines, let's say like this, and some other set of phase lines like this, right? So in general, what we want to do is to set these things up so that if we have a little change in this let's say K final, it's in this direction. That is to say, any change in K and KF which causes some scattering to occur is parallel to the constant phase line. And if we do that, then we'll be in this situation where we can focus these phonons. Let me show you how that works. Here is the Ki. Now I've used capital Ki to indicate that this is the most probable value of Ki, and I've used K big F to indicate that this is the most probable value of Kf. And here's the most probable Q vector here. Now I'm assuming that I've set up my triple axis spectrometer so that I'm looking at a phonon when I've got my instruments set up like this, where the Ki and Kf give me this Q0 vector. Now there's something called a scattering surface, and the scattering surface essentially. Let me see, did I write that down? Apparently not. So what you want to have happen is that for some neighboring value of K little f, so this is another wave vector that's going to get through your instrument, that that you're going to get scattering from the same phonon when you have this value of Kf. And you can see that if the values of Kf lie along this red line here, right, for scattering from the phonon, then you're going to have the same spin echo phase, because the only component of the wave vector that you're encoding is this component, the one that goes the component that's perpendicular to the boundaries. So effectively, you can think about this, if you like, the scattering surface as saying that if I'm looking at a phonon here at some position Q0, and now I have some change in angle of the exit wave vector. So the exit wave vector is somewhere along a line that's along here. How long does that line have to be? Well, it has to be such that the energy difference between this k little f and ki is the energy of a phonon at this point. So this scattering surface, if you like, defines what the phonon dispersion relationship looks like in this space. And so if I set the whole thing up in this way, with the angles chosen in such a way that the faces of these or the boundaries of this field are perpendicular to the scattering surface, then I will have achieved this situation in which the phase, the lines of constant phase, are parallel to the phonon dispersion surface. And then when I do the Fourier transform, I'm doing the Fourier transform perpendicular to the dispersion curve and not in some odd direction, which won't give me anything useful. So that's how that works. This is an example of an instrument that does that. You remember we talked about this neutron resonance spin echo system last time, and that system consisted of some coils that produced a constant magnetic field plus an RF field. And these coils, if I can get the arrow back, these coils here and here and here and here are these neutron resonance spin echo coils. This is a standard triple axis spectrometer, so the monochromator is back in here. The neutron beam comes to the sample, which is in this cryostat, gets scattered along the scattered beam, the KF direction, into an analyzer crystal and then into a detector here. Now, what you may remember from our discussion of neutron resonance spin echo is that the field had to be zero between these coils. And so this here is a mu metal box with the top taken off, in fact, but the top has been taken off so that you can see these coils, and normally the top is on so that there's no field, there's zero field in this region. And you can see that these coils are parallel to each other. That means that effectively the field boundaries are parallel to each other, but that they've been set up at some angle to the incident beam, and that these guys have been set up at an angle to the exit beam, and they've been set up in such a way that the Fourier transform is going to be done perpendicular to the phonon dispersion curve. Okay, so that's phonon focusing and the use of tilted fields for that. In fact, as I said, it's inconvenient to use tilted fields, or fields with tilted boundaries. So you notice this is nothing like the solenoids that were used on the normal spin echo machine. This is a neutron resonance spin echo method, and it's just much easier to change the field boundaries to be non-perpendicular to the neutron wave vector using NRSE. So now I want to talk a little bit about a use of tilted fields which has nothing to do with energy transfer. What we're going to do now is to use it to do essentially small angle neutron scattering. This slide just has a excuse me, bunch of pictures of various things that you could imagine that you might do small angle scattering on, with length scales varying from, let's say, 25 nanometers up to something like 5 microns. I don't know whether you've talked about small angle neutron scattering yet, but small angle neutron the traditional small angle neutron scattering is sort of capable of getting to a length scale of about maybe 1 micron if you really push it. So what I'm going to show you is how you can use these tilted fields to extend the length scale actually quite a bit beyond 5 microns. People have done up to 25 microns, in fact. So let's talk a little bit about, I've said some of this. You know already that I'm sure that in all conventional neutron scattering instruments, the better the resolution you get, and this is true of SANS. In other words, the better the Q resolution that you have in SANS, which translates into the better the real space resolution, the less the signal is. And the signal is less, of course, because of these boxes that I drew at the end of the wave vectors to draw the transmission function. The smaller you make those boxes, the smaller you make the transmission function, and so the less neutrons there are inside the transmission function, the lower the intensity. You have good resolution, but eventually you have no neutrons left. And in fact, on conventional SANS instruments, it's this conundrum here, this spatial resolution inversely proportional to intensity, which is what makes the SANS instruments that you see so super long. You'll see them at 20 meters long. And the reason for that is if you want very good angular resolution and you want a sample which is a sort of reasonable size, let's say a centimeter, then you have to increase the distances between all of the components in order to get good angular resolution. And I said this already, that the length scale on a conventional SANS instrument is limited to about a micron. Another issue that may or may not be of importance is that what you're really interested in is correlations in real space. In other words, the density correlations in real space. And what you measure with SANS is actually something in reciprocal space. And that may or may not be important. There are cases where, so correlations exist in real space, and then they're Fourier transformed to give you the pattern that you see in Q space. And there are cases when you do a Fourier transform from one space into another that you see different things. An example might be the RKKY interaction in materials. The dielectric function of a metal has a very weak logarithmic singularity at the Fermi surface that is very hard to see in reciprocal space. But when you Fourier transform it, you get a cosine over R cubed oscillation, which is very easy to see in real space. So there are times when it would be better to be able to measure in real space rather than reciprocal space, and times when it would be better to do it in the inverse way. Another issue that you have with SANS is multiple scattering. If you, in general, those of you who've done SANS experiments will have noted that you have to restrict the strength of the scattering to about less than 10% of the incident beam. If you have much more than that, what happens is that the singly scattered neutrons have a high probability that they'll get scattered again, and these so-called multiple scattering corrections distort the scattering curve quite a bit, and that distortion is quite difficult to deal with. And also, of course, what this means is that you start out up here with good resolution and being correlated with poor signal intensity. So you might say, okay, let's put plenty of sample in the beam and get good signal intensity, and then we can increase the signal intensity that way and afford the good resolution. Well, you can't, because if you put a bucket of sample in the beam to get lots of intensity, you'll get multiple scattering, and you can't correct the data. So these are some of the issues that you face with conventional SANS, and what I'm going to show you is that spin echo can help with some of these issues. So let's look at this situation here. Go back to our tilted field geometry. So what we have is a neutron beam coming in from the left. Our standard pi/2 coil, remember we talked about that in normal spin echo. It's the coil that starts the precession, if you're thinking about this thing in classical terms, because it brings a spin down into the plane perpendicular to the magnetic field, so the spin starts to precess. And now we're going to have this tilted field, and so instead of having the field boundaries perpendicular to the neutron beam, they're going to be at an angle to the neutron beam. And then this is a small angle scattering geometry, so you have a small angle of scattering here of theta, and you put a tilted field in the final direction, in the final beam as well. You have your pi flipper in here so that these two fields can be in the same direction. And then finally you have a pi by 2 flipper at the end so that you can measure the polarization. It's clear that any neutron that is unscattered is going to echo. So if I go through along a straight line, there's no sample here, I go through in a straight line, the length of the path in this field is going to be the same as the length of the path in this field. I'm going to assume that the two fields are equal and equal size. So the the phase angle, precession phase angle in this beam is going to, in the incident beam is going to be the same as in the outgoing beam. It's also clear if I take any sort of off angle. So if I go through along a straight path, but it isn't straight down the middle here, it's tilted off at some angle like that, I still echo. So in other words, what we're saying here is that the echo is really quite insensitive to the divergence angle of the neutron beam. As long as there's no scattering in here, I will echo. So let's look at what the precession angles are for in the incident beam and in the scattered beam. Here we have the precession angle in the incident beam. It's just this canonical, some constant times b times this perpendicular distance here divided by k sine chi, where chi is this angle here. Now, in the scattered beam, of course, the chi angle gets replaced by chi plus theta, where theta is the actual scattering angle. And remember that the polarization that I'm going to measure is just the cosine of the difference between these two. So if you go into the small angle approximation and you say that theta is small, and you expand sine chi plus theta as sine chi cos theta plus cos chi plus sine theta, and then do it in to lowest order, what you'll find is that you'll get that that expression that I've given you here, that it's cosine of this junk here times theta, and of course the q, the scattering vector, is just proportional to the scattering angle. I have that q is equal to 2 times the 2 times the wave vector. Let me be careful here. 2k times theta, where this is theta, is the total scattering angle, and so I can just substitute for theta in terms of q and get this thing down here. Now, the total polarization that I'm going to measure is, this is the polarization for one neutron, if you like, because I've just taken cosine of the Lamar phase for one neutron in the initial beam minus the final beam. But I'm going to have to add all of those up, and I add them up times the weighting factor, which tells me how likely it is that I'm going to get some scattering event with wave vector transfer q, and that's just the S of q that you've seen before as the elastic scattering cross-section. And then I'm just going to integrate that over all q. So just coming back to what we talked about, the scattering triangle that we talked about before, I have this general one here. What we now have in this situation with CSANs is we're doing elastic scattering. So we're doing elastic scattering in which the kf and the ki are equal. And I still have these sort of regions of space where in the wave vector space that can be transmitted through the instrument. This is my Q0. But now what I've done is I've set the boundaries of these magnetic fields up in such a way that the lines of constant phase are like this. So the lines of constant phase are now perpendicular to Q0, and so I'm doing a Fourier transform. Doesn't have anything to do with energy now. I'm only doing the Fourier transform in some Q direction, which I'm measuring. So what I'm saying now is that the echo polarization that I get in this so-called C-sands, spin echo sands, is proportional to the Fourier transform of this of S of Q, and the length in here. Remember the last time when we did it in energy, we had something called a spin echo time. Now I have something called a spin echo length, which is this constant here, and so I need to figure out what the magnitude of that is to figure out what length scale I'm probing in the system. I want to give you a little demonstration of how this works if you think about things in quantum mechanics. And to do the quantum mechanical demonstration, derivation, let me go back and talk about optics. So imagine that you had two calcite prisms here. You may or may not know that calcite is birefringent. It has different refractive indices for light that is polarized parallel to its hexagonal axis and perpendicular to it. And those two rays, one of which is polarized parallel to the so-called optic axis, is called the ordinary ray, and the other ray, which is polarized perpendicular, is called the extraordinary ray. And so these two rays with different polarizations have different velocities in a calcite material. So supposing I take an unpolarized light beam and I stick in a polarizer that's at 45 degrees. So that the ordinary ray, let's say, would have a polarization that's vertical on this slide, and the extraordinary ray would have a polarization that's horizontal on this slide. Then, of course, this polarization at 45 degrees I can think of in terms of a superposition of two plane waves with mutually perpendicular polarizations and in phase with each other. So what I've got is I've got I can think of this as two plane polarization states coming into this crystal. And what's going to happen is when I get to this boundary, because the boundary is tilted, there's going to be a different refraction for the ordinary ray and the extraordinary ray. And so what will happen is, let's say that the ordinary ray does this, and the extraordinary ray does the blue thing down here. And then if I stick another calcite crystal in here, I'm just going to do exactly the same as I did over here, but backwards. And what's going to happen is that the ordinary ray and the extraordinary ray are going to come out parallel to each other, but now they're going to be separated in space. So actually we have a little demonstration. I'm not going to show it to you today, with a laser and a couple of calcite crystals and a piece of Polaroid. And because the laser, of course, produces a very narrow beam, you can actually see the separation of the two rays. In fact, if you work through it, you'll find that these waves are no longer in phase. The wave fronts, as you can see here, are of the red wave and the blue wave are out of phase if you do this, whereas over here they were in phase. So now you can do the same thing with neutrons, and what you do with neutrons is you take a magnetic field over this triangular region here, and as we said when we were talking about regular spin echo, magnetic fields are birefringent for neutrons. The up state and the down state have different potential energies, different Zeeman energies, so they have different kinetic energies. Different kinetic energies means different velocities, and that's what you mean by saying the thing's birefringent. So now instead of our 45-degree polarizer, we put in a pi/2 flipper here, which produces a linear combination of up and down states. So instead of a linear combination of ordinary and extraordinary rays as we had in the light case, we have a linear superposition of up and down. Same thing's going to happen though. One state is going to get refracted differently from the other state, and then if I put in another magnetic field, they're going to come out parallel to each other. What you can find out if you just use Snell's laws, and you don't need to know anything about neutrons, you just use Snell's law, what you can find is that the change in phase here, delta phi, or delta psi, excuse me, due to any change in this angle here, is just equal to this constant, 2 pi over lambda. Lambda is the wavelength of whatever radiation you're using, times the separation between these two states. So now, if I let me do something else. Let me just finish this. I'm not going to be able to finish it. So let me go back to here. So let me go to the blackboard and show you what this is. So if I have this statement here that the change in the phase of these waves with respect to change in the angle is equal to 2 pi z, where the z is the splitting between the waves, and lambda is the wavelength of the neutron. Now, remember that what's going to happen in my scattering experiment is I'm going to change the direction of the neutron. So I'm going to change the angle at which the neutron is incident on something. And so if I call this the scattering angle, what I'm going to have is that the change in the phase of the wave is just going to be equal to the scattering angle, delta phi, which times 2 pi over lambda, times this z, this separation of the two states that I talked about. And this thing is just the wave vector transfer. So I have then that the phase change between the two waves is just q times the separation between these two rays that I drew for you. And this you'll recognize as exactly what I had when I did the classical derivation. In other words, the cosine of this is the polarization that we were talking about in this class. So this was the classical derivation of it, talking about precessing neutrons. And you can see that what I needed was this phase, which I happen to call psi on the view graph, the next view graph, and I get exactly the same thing as I got here, except now I have a definition of what the spin echo length is. The spin echo length is now the separation between these two rays. In other words, it's the distance between the up state of the neutron and the down state of the neutron when they reach the sample. I just wanted to show you that that you can do this has an analogy in a light microscope called a differential interference contrast microscope. What you do in the differential interference contrast microscope is you take these calcite prisms that I showed you, but you use two of them, and you use them stuck together so that the principal optical axes are actually perpendicular to each other. And all that does is to double the amount of refraction that you get at this hypotenuse here. So the refraction is double what you get with a single prism. So what you do is you have your light source, your point source. You have a polarizer. This is your 45-degree polarizer. You send it through this thing called a Wollaston prism that refracts the ordinary and extraordinary rays differently. You send it through make the light parallel again by using a condenser, send it through a sample, and then invert the whole thing. And what you get is a sort of a phase contrast enhanced image, because you're sending these two beams through the sample at different positions, and when they come back together, they will report on the difference of phase that they've seen as they've gone through the sample. And you can see that this is some algae, which are generally pretty transparent, but they've got these enhanced edges here, which is due to this phase, so-called phase contrast, because these two different polarization states visit slightly different locations in the sample, and then report on the difference between the phase that they saw. And so you can do this with neutrons, as I said. And now with neutrons, instead of using this this Wollaston prism made out of calcite, in which the two optic axes are perpendicular to each other, you can do something really simple, something that one of my students called a bad 5th grade science project, where you wind two triangular solenoids with fields in opposite directions. And of course that means that they have opposite, there's going to be some refraction at this place here because of the fact that the Zeeman energies will be different for the different spin states in these two because the fields are in opposite direction. Now this box here, which we've taken the top of, is just a mu metal box that makes sure the flux, magnetic flux comes around and goes back through the coil, so it effectively makes this into an infinite solenoid with a constant field. It turns out that's not a particularly good geometry, and this is what we now use, where there's this is a gap which the neutron goes through, and that gap is in this face here, so the only wire that the neutron goes through is on this hypotenuse here. And then there are various water cooling things that we need to do. Effectively then, we can set up this, this system, these pair of neutron Wollaston prisms, in the following way. We have our pi/2 coil here, which produces a linear superposition of up and down. We get the refraction here, get them back together here, just as I showed you, and then we undo the whole thing at the back end. You can see this is very similar to this tilted field that I showed you. If you were to subtract off the, so let's supposing this blue is a field of plus 100 in some units, and the purple is minus 100. So let me go into find the 0 as minus 100, then this thing goes away and all I have is 200 here, and I have 200 here. And since nothing happens to the refraction at these perpendicular boundaries here, I could fill this piece in with a 200 field if I wanted to, and that would be the parallelogram field that I showed you back here. Right? So back here, I showed you a parallelogram field, and so what I just tried to indicate to you is that this thing here is exactly the same thing, except now I've got a way of changing the size of my parallelogram because I've got a thing which is a unit here and a thing which is a unit here, and I can pull them further apart. And of course, if I pull them further apart, this distance, this spin echo distance here will change because these two are diverging rays here. So that's how you do this spin echo scattering angle measurement, which is what we call it. Most people, this is sort of general term for various ways of various experiments in which you code the wave vector. And in fact, these are the two principal ones which are done. One is called a C-SANS, which is the small angle scattering, which is what I just showed you a few view-graphs ago. But you can also do the same thing by resolving the scattering from a surface. And that's really similar to grazing incidence SANS, except that you're using spin echo to code the scattering angle. If you go through all of this, it's not particularly difficult. What you'll find is that that you can. So here's the scattering cross section that you know and love. This is basically S of Q, and I'm going to do a Fourier transform of it in the y direction, and I'm going to integrate it over the perpendicular direction because I don't have any collimation, and that's sort of going to be what I would measure, what I've told you would measure as the polarization. But it turns out that the actual echo polarization you measure is given by this exponential of this thing. If these things are small, right, then I can expand the exponential, and my polarization is going to be linearly dependent on this thing. But if I have a multiple scattering, it turns out that gets automatically taken into incorporated if I just put this exponential in here. So I measure a polarization which is given by an exponential of this g and I apologize again, I've changed notation on you from z to this psi. This is the spin echo length because it occurs over here, right? And so this is a correlation function in real space that I measure because psi is a real space distance. It's a correlation length. It's the z that I had before. It's the separation of the two spin states. And so and it's defined by this quantity here. So what I do in this CSANS technique, and we're almost running out of time, so I'm not going to belabor the point, is I measure a neutron polarization, and the neutron polarization is given by an exponential of this difference between these two correlation functions. This thing is just a normalization, if you like, to get the normalized polarization. And the correlation function that I'm measuring is just the Fourier transform of S of Q in some particular direction. So CSANS is measuring for me, if you like, a correlation function which is a Q Fourier transform of the scattering function. It turns out that this spin echo length is only very weakly dependent on the beam collimation, as I sort of indicated to you earlier. And in fact, if you want an expression for the change in spin echo length as a function of this, this is the tilt angle here of the boundary to the field. This is the expression for it. So let me just try to motivate for you what, in the last quarter of an hour, what CSANS measures. What you're really interested in, let's take a simple system which has, let's say, two phases. So you've got imagine just to be concrete that you've got little spheres in water. So this is basically paint. And what you're interested in measuring is this Debye correlation function, which is the density of material at some position r primed, multiplied by the density of material at some position r prime plus r, integrated over r prime. That's the correlation function that will tell you about the statistics of this system. If you do regular SANS, what you will do is you will simply make a Fourier transform of this thing. In fact, it turns out to be a zeroth order Bessel function because of some normalization things that happen. But so this is the intensity that you will measure in a SANS experiment. It's just the usual d sigma d omega that you measure as a function of Q, and it's the Fourier transform of this correlation function. In CSANS, it turns out that this G that I told you about on the last view graph, this G here, this one that I measure, is actually a different transform of this Debye correlation function. It's called an Abel transform. It's related to the transform that you get if you do radiography. So let me show you that. I think did I have a view graph for showing you that? Yeah, maybe I do. So the Abel transform is just a projection. Let me show you here. So this is just a projection of this function onto one axis. And it's the same sort of projection that you get if you do a radiograph. That is to say, you integrate all of what you're seeing along a particular line here. So not to belabor that point, let me just say that the Debye correlation function, this correlation function we measure with CSANS, and the intensity you measure with SANS are all related to each other. So you can see the Debye correlation is related to what you measure in CSANS by this Abel transformation. The stuff what you measure in SANS is related by a Fourier transform, and not surprisingly, these two are related by another transform called a Hankel transform. So I think that we're running out of time here. So I'm going to, I think, so I want to show you I think what a typical, okay, so let me show you this. If you measure that sort of system of spheres in water that I just the notional system that I just showed you, the correlation function that you measure, if these spheres are hard and there's no stickiness to them, is the solid line here. So this is basically a projection of the Debye correlation function. Now imagine for hard spheres, so the spheres can't penetrate one another. Now imagine you put a little sticky potential on the surface of the sphere and ask what happens. What happens is that there's more probability that the spheres will be close together. So this first dip here, you can see the first dip occurs where the distance between the spheres is sort of something between 1 and 2 times the radius of the sphere. You can see that this dip starts to fill in. So the deeper you make this sticky potential, the more probability, in other words, this curve goes up here, the greater the probability that the things will stay close to each other. So you might ask, okay, so supposing I were to measure this, this is what I would measure with sea sands. What would I see if I did that with sands? Well, here are the two equivalent sands patterns. The black curve here is for hard spheres, and the dotted curve is for this case where you have sticky spheres. And this green region here is notionally where your beam stop would be for a sands experiment. And you can see that it gets to be quite hard to distinguish between these two cases. What you will find, if you look in the literature, is that whenever the small angle scattering starts to turn up like this, people will say, oh, that's just aggregation of the sample, and we don't care about it. Well, it might not be. It might actually be something that's happening at very close range, which you would see in the sea sands picture, but you would probably misinterpret if you had the sands picture. And so what I want to try to point out to you is that there can be real advantages of measuring in one space rather than the Fourier inverted space. The same thing is true of classical traditional spin echo. Normally you measure S of Q and omega in omega space, in energy space if you like, but in traditional spin echo you measure I of Q and T, the intermediate scattering function, which is a function of time. So you have these two Fourier variables, energy and time, and sometimes you can see things in one which you can't see in the other. And here you have the same thing. You have these two spaces, reciprocal space and real space. And what I'm showing you here is sometimes it's better to measure in one space than the other. So I think with that, rather than going through, so let me just go through this last view graph here. There are some advantages to sea sands. You get real space information. You don't need to collimate the beam, so you can get higher signal intensity. If you do it with time of flight, you can measure all of the length scales simultaneously because your scanning variable is essentially wavelength. And if you look back at the expression for the spin echo length, you'll see that that scales as a square of the wavelength. It turns out you can access a much larger range of length scales than you can with conventional sands. You can go from about 20 nanometers up to 20 microns. You might be able to go lower than this, but nobody really wants to because you can do that easily with sands. This exponential factor that I showed you, this e to the g of z, automatically accounts for multiple scattering and still provides the pair correlation function that you're looking for. And because it automatically accounts for multiple scattering, you can put a bucket of sample, not really a bucket, but you can put a lot more sample in the beam, and you're not limited to having scattering probabilities of less than, let's say, 5 or 10%. And essentially, the reason, another advantage is that there's no beam stop in the sands experiment, sea sands experiment. You're measuring the main beam and the scattered beam at the same time, and so you don't have some part of reciprocal space or real space that is hidden for you, which you do in a normal sands measurement. Now, it turns out there are some disadvantages to CSANs, and that is, again, as I said, there's a complementarity between what you want to measure in one space and the other. It turns out that CSANs is very good for measuring correlations, but it's not very good at measuring the size of monodispersed particles. And that's because if you look at the SANS pattern for a set of monodispersed particles, it has some very distinct oscillations in it. And from the period of those oscillations, you can get the size of the particles very accurately. So here's a sort of comparison of what you see in SANS and CSANS. Normally, if you do a SANS experiment, you'll plot the data like this, and you'll maybe go into this low Q region down here, the so-called Guinea region, to get the radius of gyration of your particles. But in fact, if you plot this whole thing on a log scale, there are these oscillations that I talked about in the scattering down here that also give you the same information about the size of particles if you've got monodispersed particles. A typical CSANS curve is going to look like this for dilute solutions of particles, and in fact, the place at which the signal saturates here is in fact equal to the diameter of the particle. So you can see that there's some uncertainty in that because this curve comes down here and just sort of fades off into something constant here. So that's the diameter of the particle. It's not a very good diameter determination, as I said before. So for measuring the size of monodispersed particles, you're better off doing that in Q space than you are doing it in R space. If you're looking at correlation, on the other hand, as I already showed you, the correlations show up quite prominently in R space, but might be misinterpreted in Q space because you'd say it was due to aggregation or something else. Here are a couple of instruments. This is one that we've set up at Asterix at Beamline at Lance, and as you can see, this whole thing is built by graduate students. This is the few $1,000 version. This is the few $1 million version at ISIS with some very spectacular RF coils and so on. But essentially, the thing is essentially what I showed you, these Wollaston prisms separated, except that they do this by a different, slightly different method. This is a very nice instrument, don't get me wrong, but it's also much more expensive than doing it this way. So let me conclude by saying that spin echo, both in its traditional version where you're measuring energy or measuring time, the Fourier transform in energy of something, so you're measuring the time dependence of the dynamics, or in this thing that I've been talking about today, the CSANs, spin echo provides a way to separate the actual resolution you get from your scattering experiment from the amount of monochromatization you do of the beam and of the beam divergence. And so with that, let me quit and see were there any questions from the outlying sites. Colin, do you have any questions at your end?
Okay, can you hear us?
I can hear you, yes.
Okay, so let me ask one question, which is that I've heard about the CSANs for some years. Now I see these nice instruments. What is the status of users being able to actually do experiments using CSANs? And are the papers beginning to come out using this technique? I'm just interested what the status is implementation-wise.
Yeah, that's a good question. Papers are beginning to come out, especially from the ISIS instrument, because they do have a regular user program. And they're beginning to come out both on CSANs and on Surgis. Our group has contributed to that. The Asterix spectrometer, which is shown on the right here, is going to get some dedicated coils. In fact, they'll be installed this December, and of course our group has been the only one that's been using Asterix because this is our equipment up until now. But when those dedicated coils are installed, users will be able to do it. And in fact, the first user experiment will be done by some folks from Argonne in December as well. So yeah, things are beginning to come out from, especially as I say, from the off-spec instrument because it has a full user program.
Thank you.
Other questions? If not, I guess I'll thank you for your attention over the last 4 lectures and wish you luck in the rest of the course.